In this video, we're going to find an equation of a plane that contains point P and line L that's given here in symmetric form. So first thing we're going to do is make sure, check, verify that point P does not lie on line L. For point P, its x coordinate is 1, its y coordinate is -1, and its z coordinate is 2. We're going to plug those into x, y, and z in line L, or just x and y. That's all we need. We plug in 1 for x, we get 1 minus 2 over 2, which is -1/2. We plug -1 for y, we get -1 plus 3 over 1, which is 2. Since they're not equal to each other, there's no need to test z. P is not on L. And that's important, as we'll see in just a minute. We also want to acknowledge here that we'll need another point on L, or a point on L. So point Q with coordinates 2, -3, -2 is on L, again, because when we plug in minus or 2 for x, -3 for y, and -2 for z, we get 0 for all of them. And that means that the point 2, -3, -2 does lie on line L. So having done this preliminary work, let's take a look what we have. Since P is not on L, we can draw a picture something like this. Here's P and here's L. And together, a line and a point not on the line determine a unique plane. So since P does not lie on line L, P and Q together, or P and L together, will determine a unique plane, and the equation of this plane is what we're after. Okay, so the plane, there's only one plane that will contain line L and point P. So there are several approaches of finding the equation of this plane. In general, to find an equation of a plane, we need two things. We need a point on the plane. Any point on the plane will do. So here's the summary. We'd need a point on the plane, and we also need any normal vector to the plane, any non-zero vector that is perpendicular to the plane. So any vector n, which is not the zero vector, and perpendicular to the plane. So we already have point P that we know is on this plane. So we have a point on the plane, and that of course is point P, or point Q is also on the plane since it's on the line, and line is on the plane. And so we can find a third point. So here we have 2. We can find a second point on the line, call it R. So second point on L, call it R. And that would make it 3 points on the plane P, Q, and R. And then we can proceed and find an equation of a plane that contains three non-collinear points. We did an example like this earlier where we found equation of a plane that contains three non-collinear points. So this is definitely a good approach, but in this video we're going to take a different approach. We did an example like this earlier, so you can watch that video, but in this one we'll do a different approach so you have a variety of ways of solving such problems. So we're going to use the following method. Let me draw the plane or representation of the plane again. There's our point P. There's line L. And we know from the equation of line L a vector that's parallel to this line. So vector V, which has the components 2, 1, negative 2, is parallel to the line. And that's because from the symmetric equation of the line, I'll write the equation right here, x minus 2 divided by 2, y plus 3 over 1 equals z plus 2 over negative 2. So it's the denominators, 2, 1, 2, 2, 1, negative 2, that are the components of a vector parallel to the line. And there is our point Q, representation of Q that lies on the line. And let's form a vector PQ. So vector PQ, remember, is with initial point P, whose coordinates are 1, negative 1, 2, and whose terminal point is 2, negative 3, and negative 2. So vector PQ is equal to, has the components of 1, negative 2, and minus 4. And now let's draw vectors PQ and V together with the same initial point P. So here's vector PQ, and we're going to move V so that it starts at P. There is vector V. Both of these vectors lie on the plane whose equation we're looking for. And if we take the cross product of vector PQ with V and call it N, you can see N looks like that. N equals to PQ cross V, and N will be perpendicular to PQ. It'll be perpendicular to V, and it'll be perpendicular to the plane. So this vector N is what we need for the final piece of information that we need to find an equation of this plane. Okay, so let's take the cross product. That should be easy. Of PQ with N or V. You can also do V cross PQ. You get the same answer. Okay, so we write down, here's vector PQ in the second row, 1, negative 2, negative 4. And we write vector V in the third row with components 2, 1, and minus 2. And you should check that the cross product of these two vectors is a vector 8, negative 6, and 5. And now let's take either point P or point Q, which are both on this plane and find an equation of the plane that contains point P and perpendicular to the vector n 8, -6, and 5. So recall that would be 8 times x minus 1 minus 6 times y plus 1 plus 5 times z minus 2 equals 0. And so then we'll pull the variables together. This will be 8x minus 6y plus 5z minus 8 minus 6 minus 10 equals 0, or 8x minus 6y plus 5z equals to 24. And that's the plane that contains point P and contains line L.